Today we will start a new lesson, that is wave optics. So far we discussed about ray optics. There we considered light as a ray and discussed various phenomena such as reflection and refraction. And here in this video we will discuss about the wave optics, introductory part of wave optics. So first of all we will discuss about the different theories related to nature of light. Related to the nature of light, different theories are there. The first theory is introduced by Isaac Newton, that is known as corpuscular theory. He considered light as elastic, perfectly elastic balls. So whenever reflection is taking place, it is entering to that surface, and from that surface it is getting bounced back like an elastic ball. If a ball is reaching on a surface or a ball, what happens? That ball will be bounced back. If it is perfectly elastic, there is no loss of energy. So like that, Einstein considered light as elastic balls. So that light particles, we call it as corpuscles. Okay. So by using this theory, he could successfully explain the reflection and the refraction. But at that time, there are certain phenomena were observed, like that interference, diffraction and polarization of light. Those phenomena could not explain by using corpuscular theory. That time, this is by Newton. That time, Huyggn introduced the wave theory. Wave theory of light is introduced by Huyggn. So by using Huyggns wave theory, what he suggested is that he considered light as a longitudinal wave which travels through all-pervading medium, and he called that all-pervading medium as ether. Okay. He called the all-pervading medium as ether, and he suggested that light can be imagined as a longitudinal wave which travels through all-pervading medium ether. But later on, Augustine Fresnel and Young proved that light is not a longitudinal wave, but it is a transverse wave. So by considering it as a transverse wave and by using Huyggns theory, they could successfully explain reflection, refraction, interference, polarization, diffraction. All those phenomena could be successfully explained by which theory? Wave theory of light, by the modification by Fresnel and Young. By considering light as actually it is not a longitudinal wave, they could prove that it is a transverse. Later on, next theory is electromagnetic theory. Electromagnetic theory of light suggested by Maxwell. Here he suggested, or he considered light as already discussed what is meant by electromagnetic waves. There electric field will be vibrating, magnetic field will be vibrating, and the wave is traveling perpendicular to the direction of both electric field vector and magnetic field vector. So propagation of wave is perpendicular to both electric field vector and magnetic field vector, which was suggested by Maxwell. And later on, Planck's quantum theory quantum theory by Max Planck. So here he suggested that light can be considered as, instead of wave, he considered it as a particle. Each wave packet we called it as quanta, and quantum, that particle of light, we will call it as photon. So by using Max Planck's quantum theory, Einstein could successfully explain photoelectric effect, and for that he got Nobel. So these are the history behind the different theories of nature of light. Okay, and here now we will discuss about wave theory of light. In that, the first topic that we are going to discuss is wavefront. What is meant by wavefront? Wavefront. Wavefront means it is the continuous locus of those points of the medium which are vibrating in same phase. So to understand that, first of all we will discuss an example. So if we are dropping a stone on the surface of water, you might have seen that concentric circles will be formed. You might have noticed. So in each circle, the particles are vibrating in same state of motion. No. Those who are in crust, they will be having, those particles in the crust will be having maximum displacement. Similarly, the particles in the trough will be having the maximum displacement in negative direction, and those in crust will be having maximum displacement in positive direction. So here wavefront we can define as the continuous locus of all the points of the medium which are vibrating in same phase. Which are vibrating in same. The continuous locus of all the points of medium which are vibrating in same phase. So I told you, when you are dropping a stone on the surface of water, here that point where you drop the stone, there that energy will be converted, given to the water molecules. So from there this energy will be transferred to the adjacent water molecule. So this molecule will start vibrating. So you can see that concentric circles can be seen. So the molecules, if you are dropping small pieces of paper, you can see that those will be vibrating. Or if you are dropping these thermocol pieces, you can see that thermocol pieces on this surface, on this first, you can mark it as first one. So they will be vibrating in same state of motion. Similarly here next, it will be vibrating in same state of motion. So those locus of those points. So this is a locus of the points which are vibrating in same phase. So this we can say it as one wavefront. And this we can say it as another wavefront. This we can say it as third wavefront and so on. Okay. Is it clear? This is what is meant by wavefront. So this is very important. By knowing this only we can proceed to the next topic. So wavefront, it is the continuous locus of all points. What is the speciality of those points in the medium? They should be vibrating in same phase. So if it is crust, all the points here, if so we can say that the wavefront will be those particles which are lying from the center of force equidistant. Those particles which are lying equidistant from the center of source, from the source, will be having same state of vibration, or will be having same state of vibration, or if you are joining all those points, points, if you are finding the locus of all those points, then we will get the wavefront. That's why I told you this is one wavefront, this is another one, and this is third one, and so on. Okay. So if we are considering a point source, so for point source, so we can say that this wavefront will be of concentric spheres. So if this is point source, we will get spherical wave. If we are considering three-dimensional, here it is only two-dimensional, that's why we are telling concentric circles. So if it is a point source, we can say that the wavefronts will be spherical. If it is a point source, the wavefront will be spherical. Similarly, if it is a line source, how can we get a light source? If the light is allowed to pass through a thin switch, that thin switch can be considered as a light source. So we can say that if it is a line source, the wavefront will be cylindrical wavefront, because the locus, if you make the locus of those points, you can see that it will be of cylindrical. Okay. So if it is line source, the wavefront will be cylindrical. And if it is a point source, the wavefront will be spherical. And if the source is very far away, in that situation, both spherical wavefront and cylindrical wavefront can be considered as a plane wavefront. Why? If you are considering this very far away, if you are considering, and if you are considering a path, you can see that it almost can be considered as a plane wavefront. Okay, so plane wavefront. Plane wavefront we are showing like this. It is a plane wavefront. How we can get a plane wavefront? If the source is very far away, in that situation the wavefront can be considered to be a plane wavefront, even though if it is a spherical, point source, and if it is a line source, if the distance is far away, or if you are considering, it can be considered as a plane. Okay, is it clear? And in the case of ray, here we discussed about wavefront. In the case of ray, we can say that ray will be perpendicular to the wavefront. Okay, ray will be always perpendicular to the wavefront. Okay, we can show like this. It will be perpendicular to the wavefront, and the time taken by the ray to travel from one wavefront to the another through any ray will be same. Whether it is traveling through this ray or this ray, it is immaterial. Time taken to travel from one wavefront to the another remains same. Okay, so these things you have to keep it in mind. Ray is perpendicular to the wavefront. Time taken by the light to travel from one ray to another ray remains same. Okay, and if it is a converging wavefront and diverging wavefront, how can we show? Converging wavefront means the rays are converging. So converging wavefront we can show like this from here. Okay. So we can draw rays also. Rays will be like this. All should be perpendicular. Okay. Converging wavefront. And if it is a diverging wavefront, how can we show? A diverging wavefront can be shown from here. The rays are diverging. The wavefront is diverging. So here, so this is a diverging wavefront. And for a plane wavefront, we can show, I already told you. Plane wavefront, we can show that it will be like this. That's it. Huygens principle of secondary waves. So here what Huygens principle says. So first one we can write each point on the primary wavefront as a new source of disturbance called secondary waves. So each point on the primary wavefront act as a source for new disturbance. New disturbance called secondary wavelets. Okay, called secondary wavelets. 2 times it is written. Okay, called secondary wavelets. Each point on the wavefront act as a primary wavefront. Not necessarily you can write each point on the wavefront. That's also enough. Each point on the wavefront act as a source for new disturbance called secondary wavelets. We'll discuss all those. First of all, we will write. After that, we can discuss it briefly. Okay, second one, the secondary wavelets travels with the speed of light in that medium. Secondary wavelets travels with the speed of light in that medium, and the wavefront at any instant can be obtained by drawing the forward envelope. By drawing the forward envelope, or we can say that by drawing the tangential cells. So these are Huygens principle. First one, each point on the wavefront act as a source for new disturbance. So we are considering example of a plane wavefront. So here we are considering a plane wavefront. So what it says, each point is acting as a source for new disturbance. So here we are considering, unless few only we are considering, this 2, 3 only we are considering. Okay, 4 we are considering. Okay. So each point is acting as a source for new disturbance, and these travel with the speed of light in that medium. So at any instant, at some instant of time t, after some time t, so that this point is acting as source. So spherical wavefront will be there, spherical waves will be there. So it will reach, for example, like this. So for this also we can draw. For this also we can draw like this. Actually it will be similarly. For this also we can draw that. So we got each point is acting as a source. So we are getting this, but waves are traveling from this point, and after some time t, if we want to find we can draw a sphere in such a way that its radius is equal to velocity of the light in that medium into Vt. We can draw a sphere having radius Vt. So from each point we can draw a sphere. Actually, sphere can be drawn here. We are showing it as but a path only we are showing. That's why we are getting a circular pattern. So we can get it. And if we draw the tangential envelope, what we will get? For all those we can draw the tangent. So that tangent will be the sphere. Okay. So our second. This is our primary wavefront. So our secondary wavefront. This is the secondary wave. Okay. So here all these arrows what it shows, they are showing the rays. Okay. This is for then that only third part says the wavefront at any instant can be obtained by drawing the forward envelope or by drawing the tangential surface. If you are drawing tangent to each surface, if you are drawing it, we will get the secondary wavefront. Okay, is it clear? This is for plane wavefront. If it is of spherical wavefront, also same way we can draw. So each point is acting as source. So here we can draw like this. So if you join all those, we will get the spherical wavefront at any instant. Okay, so this is the way of drawing wavefronts. Okay. So, those three principles, it is very simple. First one, what says each point. If you are considering a primary wavefront, each point is acting as a source for new disturbance, and those new disturbance is called secondary waves. And these waves, from those waves will be producing, from those points, waves will be moving. Those waves are traveling with the speed of light in that medium. And to get the secondary wavefront, to get the wavefront at any instant of time, we have to draw a tangential surface. First we can mark all those wavefront waves, and if we are drawing tangential surface to that, we will get the spherical wave. Sorry, we will get the wavefront at any instant of time. If it is a plane wavefront initially, after some time also we get a plane wavefront. If it is spherical, we will get after some time we will get a spherical wavefront. Okay, so these arrows shows the rays. Now you may think that here we don't only forward envelope. Why backward envelope is not there? Backward envelope is not there because the amplitude of the wave, it is directly proportional to 1 plus 4. Amplitude is directly proportional to cos theta, and in forward direction theta is 0 degree, in backward direction theta is 180 degree. So cos 180 is minus 1, so 1 plus cos theta you will get it as 0. So amplitude of the wave in backward direction is 0. That's why it will be always moving forward direction. No backward wavefront will be there. Okay, is it clear? So today we discussed about different theories of light, and then we discussed what is meant by wavefront and Huyggns theory, that those three principles we discussed. I hope all of you understood. If you are having any doubt, contact me.